Imagine this traveller in the soft quiet of your night the universe has guided you here, as if this story was meant to find you. Just 3 days ago, a solar flare carrying billions of tons of plasma struck a precise point in space, and 3I Atlas absorbed it. The energy didn't scatter or fade, it simply vanished. Moments later, the object began to accelerate, moving faster than any interstellar visitor should ever move. What are the odds of that a silent wanderer gliding past Mars, a flare consumed like a breath, a mystery unfolding in the dark? Listen before you fall asleep. The story of 3I Atlas begins quietly, almost imperceptibly, with a faint point of light moving through the crowded starfields of Sagittarius. On July the 1st, 2025, a telescope in Chile detected an object so dim magnitude 18 that it barely registered even to an automated system trained to ignore noise. It was given the provisional designation A11P3Z, just another candidate to be checked, catalogued and likely forgotten. But over the next 24 hours, observatories around the world confirmed what the earliest calculations already implied. This object was moving too quickly on too steep a hyperbolic trajectory to be a child of our solar system. Its velocity of 61 kilometers per second, combined with an orbital eccentricity greater than 6, identified it clearly as an interstellar visitor. By July the 2nd, it received its permanent name, 3 Atlas, only the third known interstellar object to drift through humanity's observational reach. What distinguished 3 Atlas from the 2 interstellar objects before it was not merely its speed or trajectory, it was its origin point. Unlike Oumuamua and Borisov, which arrived from the solar apex, the direction our Sun moves through the galaxy 3I Atlas emerged from the south from the densely populated region near the galactic centre. Against the brightness of that stellar backdrop, early detection would have been nearly impossible. Only by examining older archives did astronomers discover that the object had been present in images from late May, already glowing, already active at a distance where typical comets remain in deep, frozen dormancy. At 6.4 astronomical units, nothing should have been happening. Yet 3I Atlas was already shedding dust, already illuminated with a faint persistent coma. Even its earliest behaviour refused to align with expectations. Hubble soon revealed a teardrop-shaped cocoon of dust enveloping a central nucleus, whose size ranged widely in early estimates from 300 metres to nearly 6 kilometres. But the size, while uncertain, was not the anomaly that captured scientific attention. That came with the chemistry. When the James Webb Space Telescope observed 3 Atlas on August 6th, the spectral lines told a story that seemed to contradict every known model of cometary behaviour. Instead of water vapour dominating the emissions, the object was releasing carbon dioxide at a rate of 129 kilograms per second. The ratio of CO2 to water was 8:1, one of the highest ever measured in any comet, natural or otherwise. This alone would have placed 3I Atlas in an unusual chemical category, but subsequent observations deepened the mystery. Cyanide was detected, organic molecules, carbon monoxide, and then came the most striking contradiction: vaporized nickel but no iron. In cosmic chemistry, nickel and iron are inseparable companions forged together in supernovae, incorporated together into planetary bodies, and released together when heated. Finding one without the other breaks the rules written into the evolution of a matter. As chemical anomalies accumulated, the trajectory began to tell its own quiet, improbable story. Interstellar objects arriving from random orientations should intersect the solar system at arbitrary angles that ignore the thin plane where our planets orbit. But 3 Atlas approached at an inclination of only 5 degrees from the ecliptic, as if it had slipped into the solar system along the same highway used by our planets. The odds of such alignment purely by chance are roughly 1 in 500. Yet alignment alone could still be coincidence until the sequence of planetary encounters became clear. The object passed within 28 million kilometres of Mars, 97 million of Venus, and 54 million of Jupiter. Each of these encounters required the planets to be in precisely the right places in their orbits at exactly the right moments. The probability that a randomly arriving interstellar object would achieve this choreography through chance alone is roughly 1 in 20,000. These numbers do not prove deliberation, but they press against the boundaries of what randomness typically offers. Despite these improbabilities, 3i Atlas continued to behave outwardly like a normal comet. It developed a coma and evolving tail and displayed clear signs of volatile sublimation driven by sunlight. It rotated. It released material. Nothing about its external appearance would have suggested anything unnatural to a casual observer. But its mass implied by the absence of measurable non-gravitational acceleration, despite enormous outgassing, hinted at something far heavier than expected. To lose more than 100 kilograms of gas per second without producing detectable thrust requires a nucleus tens of billions of tons in mass. Either 3i Atlas was extraordinarily large, impossibly dense, or hollow in a way that hides a massive underlying structure beneath a thin veneer of ice and dust. The deeper scientists looked, the more the object resisted simplicity. Every explanation had a counterpoint. Every natural model required exceptions, special environments, unusual chemical histories or physical processes not observed elsewhere, and yet no anomaly alone was extraordinary enough to declare the object artificial. Instead, 3i Atlas settled into a rare and uncomfortable category, a phenomenon whose properties are individually plausible, but collectively improbable. In the quiet space between data points and interpretations, astronomers found themselves confronting a question older than science itself. What do we do when the universe presents us with something that may not fit any of our pre-existing assumptions? Do we force it into our models, reassuring ourselves that nature is merely being creative, or do we allow ourselves to consider the possibility remote, unproven but not forbidden, that we may be witnessing something constructed rather than formed? For now, the evidence remains ambiguous. The universe often speaks in riddles and thrashil. Atlas may be nothing more than an especially strange comet drifting through the solar system after a long journey from another star. Or it may be something older, something built to endure across cosmic time wrapped in frost and silence, as it carries a story humanity has not yet learned to read. Either way, the object continues its path through the darkness, indifferent to our questions. And we, watching from our fragile blue world, continue to follow its trail, searching for meaning in the thin light drifting through the void. As 3 Atlas continued inward, the solar wind traced delicate structures across its surface, and telescopes tracking its progress began to detect behavioural patterns that did not align cleanly with what sublimation alone should produce. The comet displayed jets, streams of gas erupting from volatile rich patches, but the primary jet, the one facing the sun, refused to rotate with the nucleus in the way most cometary jets do. Instead, it held its direction with unusual persistence, as if anchored to a fixed orientation, rather than a spinning irregular surface. For 6 weeks as the object approached perihelion, the jet remained steady. Even the natural tumbling of a comet failed to disrupt it. Astronomers offered natural explanations. Perhaps the nucleus contained an extremely localized reservoir of CO2 that maintained continuous outflow. Perhaps the rotation axis was aligned in such a way that the jet always faced the sun. These possibilities were not impossible, but they demanded finely tuned conditions. Still, no one could claim such behavior violated the laws of nature. It merely stretched them. What happened next stretched them further. On October 21st, the sun unleashed a coronal mass ejection, billions of tons of plasma thrown outward in a halo of charged particles. The eruption was immense but not unprecedented. Solar activity was rising toward its expected peak. Yet this CME was unusually directional, forming a focused cone that happened to intersect directly with the position of 3i Atlas. By the time the plasma wave reached the object, most of its energy should have dispersed into the widening vacuum. But the data told another story. Instruments tracking the comet recorded an absorption event. The flare's energy, instead of scattering, flattened out and vanished. It was as though the comet swallowed it, taking in the kinetic assault of a gigaton-scale plasma wall without the expected spike in reflected energy. The simplest explanation was instrumental error. Solar observatories occasionally misread high-intensity events. NASA called it noise and anomaly, a glitch soon to be corrected in post-processing. But 12 hours later, orbital tracking stations noticed something harder to explain away. The comet's velocity had changed small, precise and aligned almost perfectly with its direction of travel. A natural comet struck by a solar flare should not accelerate forward. Outgassing triggered by heating would push the nucleus away from the Sun, not toward it. The suggestion that this could be a fragmentation event splitting off a portion of the comet's mass would normally be credible. But fragmentation produces chaotic momentum, change is not a clean acceleration along the exact vector that maximizes gravitational benefit near solar perihelion. Still, the deviation was tiny, only a few meters per second squared, barely above the threshold of detection. Scientists stressed caution. Data this delicate often hides uncertainties. The comet was approaching solar conjunction, slipping into a region of the sky where Earth-based telescopes struggle to resolve anything clearly. There were plausible reasons to hesitate before drawing bold conclusions, yet the pattern was forming chemistry that did not match natural expectations, trajectory alignments that defied randomness, a mass that resisted known models, and now a correlation between a solar event and a forward acceleration that should not have occurred. No single fact was definitive, but together they accumulated into a quiet insistence that the universe was offering something unusual, something that required attention. As 3I Atlas neared perihelion, the geometry of observation shifted unfavourably. For nearly 3 weeks the comet would pass behind the Sun from Earth's perspective, lost in the glare of the star whose gravity controlled its path. During this period no ground-based telescope could observe it. Even Hubble and the James Webb Space Telescope orbiting far above Earth's atmosphere could not safely point near the Sun. It was a blind spot written into the structure of our solar system, a predictable eclipse of knowledge. And it happened to coincide with the critical moment when an object travelling at its highest velocity could alter its trajectory with the least energy expenditure. A manoeuvre at perihelion, whether a slight braking or a subtle thrust, could decide whether 3I Atlas remained an interstellar traveller or became a captured object bound to the Sun. The timing was again improbable. Calculations showed that for a randomly arriving interstellar object, the chance that perihelion would fall during Earth's solar conjunction was about 1 in 25, not impossible. But when multiplied by the already unlikely alignments and close planetary approaches, the odds pushed into uncomfortable territory. Still, probability alone cannot prove intent. Nature is vast and low probability events happen constantly. The cosmos does not owe humanity a pattern that fits our expectations. Mars, however, offered a brief window before the conjunction. As 3I Atlas passed within 28 million kilometres of the Red Planet on October 3rd, the spacecraft in Martian orbit ESA's Trace Gas Orbiter, Mars Express, and NASA's Mars Reconnaissance Orbiter attempted observations. The European Space Agency released a handful of faint images, a glowing dot, a soft halo, a coma consistent with volatile sublimation. Nothing extraordinary. No structures, no anomalies visible at their limited resolution. NASA's high-resolution imaging science experiment, HiRISE, should have produced the clearest images by far. Its optics are capable of resolving objects as small as 30 centimeters from orbit. It would not see structural details on the nucleus, but it could have distinguished features in the coma, offered precise nucleus size estimates, and clarified several uncertainties. But HiRISE's images were never released. NASA entered a government shutdown on October 1st. Offices closed, data pipelines froze, public repositories stopped updating. Official statements described the delay as procedural, innocent, unavoidable, bureaucratic. And perhaps it was. But the silence created a vacuum. Into that vacuum flowed speculation. Some argued that the images were mundane, offering nothing worth rushing through administrative disruption. Others suspected that something unusual had been seen, something requiring careful review to avoid premature interpretation. Both explanations were possible. Both coexisted uneasily. In the days following, the flyby amateur astronomers tried to compensate for the lack of institutional data. One astrophotographer, using aggressive digital enhancement, produced an image that appeared to show angular structures within the coma, dark geometric forms that seemed too organised to be random dust. Experts debated whether this was genuine detail or merely artefacts created by overprocessing. Pareidolia in the language of neuroscience is the human tendency to find patterns in noise, and the boundary between discovery and illusion is dangerously thin when pixels are pushed beyond their limits. Meanwhile, enhanced versions of ES's raw images began to circulate online. Some were obvious fakes. Others looked ambiguous, suggestive, uncertain enough to raise questions but not answer them. In the flood of altered images, clarity dissolved. Truth blurred with invention. And through it all, the official silence persisted. The deeper one studied the object, the clearer a single reality became through. Atlas was a puzzle composed of contradictions, scientific, statistical, chemical, geometric. Nothing about it demanded an extraordinary conclusion, yet nothing aligned comfortably with ordinary ones. It lingered in the thin space between explanations where human certainty falters and humility becomes not just useful but necessary. The universe rarely reveals its meaning quickly. Some mysteries are not meant to be solved immediately, only observed, examined, and accepted with patience. And as the comet moved behind the sun, slipping into the blind spot of our instruments and our understanding, the only thing left was to wait. When the object finally passed into the sun's glare, disappearing from every telescope pointed from Earth's orbit, the world entered a rare kind of astronomical quiet. For 3 weeks, the Rai Atlas moved through a region of space where our instruments could not follow, and in that absence of observation, imagination expanded to fill the void. Astronomers continued to calculate its path, propagating its orbit forward, using the last known measurements. The equations behaved cleanly, but equations are only as reliable as the assumptions placed beneath them. And the assumptions, gravity alone, natural outgassing, predictable physics, were beginning to show cracks. Before the disappearance, the first hints of deviation had already emerged. The comet's trajectory, which had matched pure gravitational predictions with exquisite precision for months, began to drift subtly. Only by arc minutes, then by fractions of arc minutes. Tiny shifts, barely measurable, yet unmistakably real. These residuals, insignificant at first glance, traced their origins back to the period immediately after the solar flare, the energy absorption event, the quiet acceleration, the first deviation from what a natural comet's behaviour should have been. Astronomers cautious by training offered explanations rooted in the familiar. Perhaps the CME had triggered asymmetric outgassing from a newly exposed volatile pocket. Perhaps a small fragment had broken away, transferring momentum. Perhaps the rotational state had altered sublimation patterns. All physically possible. All consistent, at least in part, with known cometary behaviour. But each explanation required the physics to arrange itself in just the right way. Not impossible, simply improbable. Still, science has always lived with improbability. Statistical outliers are expected, even necessary. If every comet behaved identically, astronomy would be a dead discipline. And so the deviations were catalogued, analysed, debated, then cautiously filed under anomalies requiring further study. An elegant way of saying we do not know, but we must pretend we do. As October waned, solar conjunction sealed the sky. 3I Atlas entered the region where even the most advanced space telescopes struggled. Only dedicated solar instrument spacecraft not designed to study comets could offer the faintest chance of observation. SOHO Stereo, a solar orbiter. Even the Parker Solar Probe each carried instruments pointed generally toward the Sun, but capable in principle of detecting bright comets passing nearby. Predictions suggested that 3 Atlas might drift through the outer edges of their fields of view, faint as dust but still traceable if the geometry aligned. Engineers adjusted exposure times, widened filters, and prepared for whatever the spacecraft might capture. None of it was certain. The instruments were built for studying the Sun and not for capturing a distant, dim interstellar visitor. Yet the hope remained that some fragment of useful data, a smear of brightness, a silhouette, a plume might pierce the observational blind spot and provide insight into what the comet was doing while hidden from Earth. Because perihelion, that moment of closest approach to the Sun, is where trajectories can be changed most efficiently. A small impulse applied near perihelion can shift a path by enormous distances years later. For spacecraft, this is a known strategy. For natural comets, it is irrelevant. Nature does not time maneuvers. But for something else, if something else existed, it would be the optimal moment to make a choice. Continue outward into interstellar darkness, or bend subtly carefully into a trajectory that remained within the solar system. With Earth blind, the timing felt almost designed. But design is a dangerous assumption, and science does not permit such leaps without evidence. While the comet slipped behind the Sun, attention shifted to Mars, specifically to the data missing from NASA's orbiters. Days became weeks, and still nothing appeared from HiRISE. The European Space Agency had released their images promptly as promised. China and the UAE remained silent. NASA, trapped in a funding lapse, was frozen in procedural silence. Scientists publicly insisted that the vacuum of information was purely bureaucratic. Privately, they were uneasy. In science, silence is rarely neutral. It gathers weight. It becomes a shape. During this same period, amateur astronomers compared notes across continents. They shared processed frames, debated noise patterns, argued over calibration methods. Their passion filled the gap left by institutional paralysis. And while most of what they produced contained nothing unusual, just faint halos, grainy smears, and the beautiful randomness of the cosmos every so often, a frame emerged with edges that looked too straight, gradients too sharp, shadows too deliberate. Some of these were illusions, processing artifacts overfitting from enhancement algorithms, or tricks of contrast stretching. But not all were so easily dismissed. A handful defied simple classification, sitting uncomfortably between natural and artificial, between noise and signal. The debate over these images did not resolve anything, but it revealed something important. The human mind is exquisitely tuned to seek meaning even when meaning may not be present. And yet, occasionally meaning truly is there, just faint enough to be doubted, just strong enough to be unsettling. By late October, the sun's glare began to thin. The comet's predicted path carried it toward visibility once more. Telescopes waited at dawn horizons, their domes opening long before the air-cooled instruments ready. Energy levels rose in observatories even as sleep levels fell. The same question lingered in every mind when Thruai Atlas emerges again. Will it be exactly where the equations predict? Would its orbit remain hyperbolic, a visitor continuing outward untouched? Or would the numbers shift? Would the curve bend? Would it be staying? The quiet anticipation of those nights felt almost sacred. Humanity does not often wait for something so vast, so indifferent, so beyond our reach. And yet we waited collectively, breath held across hemispheres, instruments, humming algorithms, prepared eyes trained on the thin line where night yields to day. When the first post-conjunction images finally arrived, faint and imperfect, but undeniably real, the tension broke into a kind of collective exhale. Thruai Atlas had returned to view. Its coma was intact. Its tail had lengthened. It looked at a glance like a natural comet completing its solar passage, but its position did not match predictions. Only by thousands of kilometers, a small error in a solar system scale, but enough to be undeniable. Enough to signal that something had happened while it was hidden from us. Enough to keep the mystery alive. The eccentricity of its orbit had changed, still hyperbolic, still unbound, but less so. A tiny shift, a subtle breaking, a decision unconfirmed. For now, all anyone could say was this: the universe had moved quietly and deliberately while Earth looked away. And whatever Thruai Atlas truly was, it had not passed through perihelion unchanged. As more observatories turned toward the returning comet, its new trajectory resolved with increasing clarity. The deviation was small, so small that a casual observer would dismiss it as noise. But astronomy thrives in the realm of precision, where millimeters become kilometers and minutes become months. The few thousand kilometers of displacement, the slight reduction in eccentricity, the nearly 50 meters per second difference in velocity, these were not statistical flukes. They were fingerprints of a force unaccounted for, a whisper of momentum applied at the very moment Earth could not watch. Predictably, explanations began to crystallize along familiar lines. The standard model of cometary physics asserted that fragmentation near perihelion could produce sudden shifts in motion. The stresses of heating can crack a nucleus, venting gases explosively and ejecting material in unpredictable directions. Such events have been seen in comets before sudden brightening, then the faint imprint of new trajectories. This explanation was plausible, But the momentum change recorded in 3 Atlas did not resemble chaotic recoil. It resembled alignment to shift almost perfectly along the comet's forward path, as if nudging its course rather than disturbing it. Some scientists insisted this alignment was a coincidence. With enough random fragmentation events, one will inevitably mimic purposeful motion. Others argued that such coincidences become statistically meaningful only when combined with everything else. 3I Atlas had already done. Its chemical mismatches, its unlikely planetary approaches, its anomalous jet stability, its directional alignment with the ecliptic. Still, the community pressed forward with caution. They reminded themselves, and the public, that a single anomaly does not justify abandoning naturalistic explanations. And yet, beneath the surface of official discourse, a quieter sentiment grew that nature was no longer behaving with the indifference that characterizes natural processes. It was behaving with pattern, with coherence, with sequence that resembled intent, even if intent was never invoked explicitly. The true turning point arrived not from Earth, but from deep space. 4 days after perihelion, the JUICE spacecraft, still far from its eventual destination at Jupiter, captured its first faint glimpses of the comet in its wide field instruments. The resolution was low, the images blurred by distance, and the limitations of a camera designed for icy moons, not transient interstellar visitors. But the data was invaluable. 3I Atlas was outgassing vigorously far more than before. Not explosively, not chaotically, but with a sustained intensity that matched the brightening reported by ground-based telescopes. Natural explanations again took the forefront. As a comet retreats from the sun, previously shadowed regions of its surface begin to warm, exposing fresh ice and triggering delayed activity. This was entirely expected, but the rate of increase raised eyebrows. Models predicted a decline in brightness post-perihelion, not a gradual rise. Even the rotation of an elongated nucleus could not produce the slow, steady surge observed. If sunlight alone drove the outgassing, its influence should have been weakening, not strengthening. Some astronomers proposed a more exotic mechanism that the solar flare absorbed days earlier had triggered changes in subsurface layers, heating them from within. This hypothesis was speculative but elegant, an internal reservoir slowly venting not in response to current sunlight, but to energy delivered days before. Others wondered whether the flare had done more than heat the object, whether the CME delivered not just energy, but information-charged particles altering magnetic fields, or interacting with ionized jets or triggering chemical transitions we do not yet understand. In essence, the flare might have acted as a catalyst, awakening something that could then sustain activity independent of solar input. Still more cautious voices noted that perhaps none of this mattered. Perhaps 3I Atlas was simply atypical, like so many interstellar objects will be. The first 3 we have detected are each unlike the others, suggesting a diversity of origins across the galaxy. With a dataset of only 3, any anomaly is magnified. Yet even these cautious voices could not ignore what came next. As November deepened, JUICE's instruments captured more detailed spectral data. These readings showed subtle but distinct changes in the chemical composition of the outgassing. Carbon dioxide still dominated, but beneath it emerged faint traces of metal oxides, iron oxide, titanium, oxide compounds that do not belong in pristine cometary ice. Metal oxides form in environments involving heat atmosphere or liquid water, none of which exist in interstellar space. These signals were weak, buried in noise, and difficult to interpret, but their presence, however faint, demanded explanation. Perhaps the comet had once passed close to a star. Perhaps grains of material from another planetary system were incorporated into its crust. Perhaps surface frost had sublimated enough to reveal deeper ancient layers with unexpected histories. And yet there was another interpretation, one unproven but increasingly whispered in careful conversations, that the metal oxides were not primordial at all, that they were remnants of something constructed, later coated with millennia of dust and ice, that the object's surface was not merely fractured rock and frozen gas, but a shell, one that had endured so long and travelled so far that the universe had half buried its original nature beneath cosmic weathering. These thoughts remained theoretical, unspoken in official discourse, but they were present quiet undercurrents beneath the public scientific conversation. Meanwhile, Earth's telescopes continued tracking the comet's motion with renewed rigour. Each new observation refined the post-perihelion orbit, and with each refinement the conclusion solidified the comet was no longer following the exact escape trajectory predicted months earlier. It was still leaving, still bound for the interstellar dark, but its departure angle had changed. A small difference in angle becomes immense over time. Extrapolated forward, the new trajectory implied that 3 Atlas would now pass remarkably close to several star systems over the next 100,000 years. Not by chance, chance rarely arranges such alignment so neatly, but by the accumulation of tiny adjustments made at the most gravitationally potent moments, perihelion and the Jupiter encounter to come. These shifts did not confirm anything deliberate, but they made it increasingly difficult to assert that nothing deliberate could possibly be happening. By late November, after the first wave of post-conjunction data, a deeper quiet settled over the scientific world. The comet was behaving in a way that refused to collapse into certainty. Neither natural nor artificial explanations had won. Both remained standing, neither disproven, neither satisfying. The universe for now was offering the rarest state of all ambiguity, a reminder that not all questions demand answers, some demand patience. And 3 Atlas, moving outward once more into a region of cold and darkness, carried that ambiguity like a trail, behind it a thin luminous thread that humanity followed with equal parts curiosity and unease. Even as the Atlas pulled away from the sun, widening the distance between itself and the instrument struggling to follow it, the object refused to settle into predictable behaviour. Its brightness fluctuated subtly across days, not with the periodic rhythm expected of a rotating nucleus, but with a slow rising undercurrent that could not be traced to sunlight alone. A natural comet should have begun dimming, now cooling as it retreated. Instead, the light curve showed a gentle ascent, as though the object's interior had been warmed in a deeper delayed way, as though the stored energy of the solar flare was still unwinding, through its structure surfacing grain by grain, molecule by molecule. Observers debated what they were seeing. Some argued that fresh ice deposits were rotating gradually into sunlight, revealing volatile material that had remained hidden before perihelion. Others suggested thermal inertia, deeper layers of the nucleus warming and releasing gas only after a time delay, a pattern not entirely unprecedented. But the increase was too steady, too smooth, too independent of the nucleus's known rotation period. It lacked the signature of sunlight. It felt endogenous. Still, science does not permit conclusions drawn from feelings. Data must speak even when it whispers. And the whisper at this stage was consistent but ambiguous. Enough to intrigue, not enough to claim. By early December, astronomers had gathered enough trajectory data to confirm that the object's motion had diverged from predictions not only during perihelion, but continuing afterward as well. Small persistent residuals continued accumulating deviations too sustained to attribute to a single event, too consistent to blame on measurement noise. Something small was continuously pushing 3I Atlas forward, nudging it along the path of least gravitational resistance. Tiny forces can reshape cosmic futures. Even a few tens of meters per second gained across months can alter a comet's course by astronomical distances over millennia. And so the new trajectory, when carried forward across tens of thousands of years, showed the object curving almost elegantly toward encounters with nearby stellar systems. Epsilon Eridani, Tau Ceti, systems that coincidentally or not are considered among the prime candidates for habitable planets. The alignment could be chance. The galaxy is vast and long trajectories inevitably intersect the neighbourhoods of stars. But the precision of the new path made some astronomers pause before dismissing the idea. The debates grew sharper, though rarely public. Most discussions behind closed doors revolved not around whether 3 Atlas was artificial that remained too premature, too inflammatory, but around the increasing mismatch between observation and cometary physics. The mass estimates remained incompatible with the measured acceleration. The chemistry continued to defy conventional models. The spatial structure of the early jets resisted easy classification. Everyone agreed the object was unusual. No one agreed why. In this uncertainty, attention returned again and again to Mars, or rather to the silence surrounding it. HiRISE, with its unmatched resolving power, had been expected to yield critical insights. Even if it could not resolve the nucleus itself, it could have captured valuable details about the inner coma particle distributions, asymmetries, structural shading, thermal gradients. The European images had shown little at their limited resolution. China and the UAE had said nothing, and NASA's data, delayed by administrative paralysis, remained conspicuously absent. Weeks passed. The shutdown eventually ended. Data pipelines resumed. Archives reopened. But the HiRISE images did not appear. NASA explained that processing had been delayed due to incomplete calibration files and disrupted mission operations. The explanation was technically plausible. Few doubted its accuracy on paper, and yet the absence persisted. Every day without the release of the images gave them weight they might not have carried, otherwise a silence accumulating, mass-drawing wonder toward it like gravity. In the meantime, amateur astronomers continued refining their own observations. A few began attempting more sophisticated stacking techniques, layering hundreds of exposures to sharpen the faint halo of light around the nucleus. Most results showed nothing unexpected, the faint haze of sublimated dust drifting outward in a soft, tear-shaped plume. But occasionally a frame revealed faint linear structures in the coma, too uncertain to publish, too provocative to ignore. Most scientists dismissed these as processing artifacts, and perhaps they were. A field as delicate as astrophotography easily conjures lines where none exist. And yet a small group of independent researchers noticed a repeating pattern. The faintest hints of geometry appeared only in frames taken after the solar flare. Before October 21st, no such features appeared. After October 21st, they appeared intermittently, never clearly enough to claim, always clearly enough to wonder. It was during this period that another anomaly surfaced, not in the visible light of telescopes, but in the radio spectrum. A brief signal lasting less than half a second was detected by the Deep Space Network. It came from the direction of 3I Atlas, though positional uncertainties left room for doubt. The signal fell near the hydrogen line, a frequency so universally significant in radio astronomy that any civilization with a basic understanding of physics would regard it as a universal channel. Yet the signal did not repeat. It flickered once, encoded faint structure, and vanished. SETI evaluated it with cautious enthusiasm. It was not ruled out nor embraced. Instruments searched for repetition across weeks. None came. The signal remained an orphan, neither noise nor message, only an unanswered question, as December deepened through us. Atlas moved steadily outward, receding from the inner planets and slipping into colder space. Its coma began to shrink. Its tail thinned. Dust that once stretched 100,000 kilometers now dispersed into the solar wind. It was becoming faint, elusive, and soon would be hard to track. But even as it faded, the sense of mystery did not, because objects of the natural world rarely challenge so many assumptions at once. Rarely do their anomalies cluster, reinforce one another, or persist across so many forms of measurement. 3I Atlas did not merely misbehave chemically or dynamically or photometrically, it misbehaved in all three and in ways that hinted at a common underlying cause. And yet within the scientific community, the most honest conclusion remained the quietest one: uncertainty. Not the uncertainty of ignorance, but the uncertainty of a universe that sometimes speaks in riddles rather than answers. The kind of uncertainty that forces humility, not theories. The kind that expands the edges of what we know by reminding us how much remains beyond reach. As the year turned, the comet drifted deeper into the dark, a dim, cold traveller pulling the questions of an entire planet behind it like a fading tail. And on Earth, astronomers kept their telescopes pointed toward its path, listening for changes in its brightness, its motion, its silence. Because sometimes the cosmos reveals itself slowly in layers, the way dawn reveals a horizon, and sometimes the waiting becomes part of the discovery. As the weeks passed and 3I Atlas moved farther from the sun, its fading light became a kind of invitation not for closure but for deeper attention. The world waited for JUICE, the ESA spacecraft, whose trajectory, by an extraordinary alignment of timing and orbital mechanics, placed it in position to observe the interstellar visitor just weeks after perihelion. JUICE had not been designed for comets, certainly not for interstellar anomalies, but it carried instruments of rare sensitivity, infrared spectrometers, high-resolution imagers, particle detectors capable of sampling microstructures in space. It was by chance or fate the nearest witness available. The first data arrived, slowly trickling across the deep void at bit rates limited by distance and antenna constraints. Scientists knew the images would be coarse. They did not expect revelation, but when the first processed frames appeared on screens in early February, the room fell silent. The nucleus of 3I Atlas was no longer a smeared point or a guessed at silhouette. It was visible, distinct, elongated, a dark spindle-like structure surrounded by the soft glow of sublimating frost. For the first time, humanity saw its true shape. The nucleus was roughly 4 kilometers long, cylindrical, rather than irregularly lumpy like most cometary bodies. Its length-to-width ratio alone placed it among the most extreme objects ever observed. Its surface was darker than typical comets, absorbing almost all sunlight that reached it. Along its length ran faint linear ridges, too straight to be fractures, too consistent to be random scars of time. They might have been geological layering, they might have been erosion channels, they might have been the gentle illusion of shadow topography. But they carried a symmetry that invited scrutiny. The dominant jet, the one that had puzzled astronomers since August, was clearly visible, emerging from one end of the elongated structure. It sprayed outward in a controlled fan stable even after perihelion, as though fueled by a reservoir oriented precisely along the nucleus's axis. Other jets speckled the surface, rotating in and out of sunlight, but this primary jet maintained a geometry that seemed too deliberate for a chaotic, icy body born in the distant cold of a random star system. JUICE's spectrometers provided the next clues. The chemical profile matched earlier observations, carbon dioxide, carbon monoxide traces of water vapour. But layered beneath those were spectral signatures of metal oxides, iron, oxide, aluminum, oxide, titanium oxide. These were present only in faint concentrations, barely emerging from the noise. But they were there, and their presence forced new questions. Metal oxides do not form in deep space. They require heat, oxygen, geological processes, or atmospheric exposure environments associated with planets, not comets. Perhaps 3I Atlas had passed near a star in its ancient journey. Perhaps collisions had heated its surface. Perhaps dust grains from some ancient debris disk had attached themselves over time. All of these were possible. None were satisfying. As JUICE transmitted more frames, more spectroscopic readings, more tiny streams of data, a kind of collective unease grew in the scientific community. Not fear, science does not fear, but the discomfort of confronting something that refuses to settle into a familiar category. A few researchers began to say aloud the question many had whispered: what if the ridges were not natural? What if the shape was not coincidence? What if the metal oxides did not represent contamination, but something surviving beneath the frost? Something old, worn by time, disguised by ice. Such conclusions were still heretical. But the possibility, once tiny, no longer felt absurd. The public, meanwhile, experienced its own shift. When ESA released the first JUICE images, the world's attention snapped back to the mystery it had begun to forget. The elongated nucleus, with its strange linear features, appeared everywhere: news outlets, live stream, social feeds. Commentary split along predictable lines. Skeptics insisted the ridges were geological. Enthusiasts declared them artificial. Scientists asked for time and data. Time and data rarely satisfy the imagination. The silence from NASA's Mars orbiter data now felt heavier. Months had passed. The bureaucratic backlog was no longer an adequate explanation for their absence. The more stunning JUICE's images became, the more the world wondered what the high-rise camera might have seen at closer range. It was not fair. Space science is slow data. Pipelines are complex and administrative disruptions leave long shadows. But fairness has never been the measure of human suspicion. While debates churned, astronomers continued tracking the object's motion. And by early March, the next surprise arrived: a faint magnetic signature detected by Juno as it passed through Jupiter's magnetosphere. Comets do not have magnetic fields. They are too small, too cold, too chemically primitive. but 3 Atlas exhibited a weak rotating field synchronized with its nucleus, almost as though something inside it carried remnant magnetization or structured metallic composition. Natural explanations again existed, but each required rare circumstances, unusual histories, or untested phenomena. Artificial explanations remained unverified, unproven, unclaimed, but also increasingly impossible to ignore. Then, as though timed for narrative effect, the comet deviated again during the Jupiter encounter. A tiny, precise acceleration aligned once more with its motion vector. A natural comet interacting with Jupiter's gravity should have followed the predicted slingshot. But 3I Atlas gained an extra 50 meters per second, not from gas jets, not from fragments, not from physics known to operate at such a scale. Scientists now faced an uncomfortable choice: decide which improbable explanation they preferred. By late March, the object had passed beyond the outer planets. It was dimming rapidly, crossing into a region where only the largest telescopes could track it. Yet even as it faded, its influence grew. Humanity debated not only what it was, but what it meant. A comet born in the far reaches of another star system was extraordinary enough, but a comet that looked layered, behaved consistently, accelerated at strategic gravitational moments, absorbed energy from a solar flare, and carried metal oxides in its composition that demanded attention of another kind. Perhaps the most profound shift was not in the scientific community, but in the quiet realization spreading across humanity: if 3I Atlas was artificial, then it was old. Older than Earth, older than the Sun. Built by a civilization long vanished a message from a time before humanity could imagine itself. Or it was natural, and the universe was simply stranger or deeper, more structurally diverse than we ever allowed ourselves to believe. Either conclusion was humbling. By April, the comet was nearly lost to the dark. Only the largest observatories could still track its retreat, and even those struggled against the faintness of its fading coma. But the questions did not fade with it. They grew sharper, heavier, more insistent. The cosmos had revealed something, not fully, not clearly, but undeniably, and humanity in its smallness felt the shift. Sometimes meaning arrives not in answers, but in the arrival of a question that refuses to disappear. And 3I Atlas, though receding into silence, had left behind a question so vast that even the night sky seemed larger for containing it. By the time the comet drifted beyond the orbit of Mars again, its glow diminishing into the texture of deep space, the debate surrounding it had spread from observatories and research centres into quieter, more philosophical circles. Scientists, who normally spoke in the careful language of measurements and uncertainties, began contemplating broader implications, not because the data demanded recklessness, but because the questions raised by 3I Atlas touched something older than science, the ancient human impulse to ask whether we are alone, and whether intelligence leaves traces beyond its lifetime. Much of this reflection gathered around a familiar framework, the Drake equation. For decades it had been the mathematical symbol of our hope and skepticism, an attempt to quantify how many civilizations might exist in our galaxy. But the Drake equation communication assumes that advanced beings broadcast information across the stars. It imagines civilizations announcing themselves through radio waves, laser pulses, intentional signals. It imagines neighbours trying to be found. 3I Atlas. If artificial suggested something very different, what if civilizations do not broadcast? What if they explore? What if they send probes small, durable, disguised as natural debris drifting silently between the stars? In this possibility lay a significant shift. Broadcasts fade, signals scatter, but objects endure. An artifact can last for eons drifting between sunlit systems on trajectories older than continents. A probe does not depend on the lifetime of its maker. It lives on inertia, on momentum, on design. If 3 Atlas was such a probe, its age alone would surpass human imagination. Analyses of its motion through the Milky Way suggested an origin billions of years ago from a region of the thick disk formed long before Earth existed. It may have been older than terrestrial oceans, older even than the planet's first atmosphere. To call it a messenger would be misleading. Messengers deliver things. This object, if built, was more like an instrument left running in the dark, no longer belonging to anyone, simply abiding by long-forgotten instructions. This idea unsettled many. It reframed the narrative of contact entirely. Humanity often imagines first contact as a moment, a beam of light, a message decoded, an encounter with intention. But what if contact is not a moment at all? What if it is an archaeological event? A discovery of something ancient that reveals not the presence of others but the memory of others? The possibility that 3i Atlas might be a relic, a technological fossil drifting across cosmic time, changed the flavour of the conversation. Suddenly the question was not whether another civilization existed now, but whether another civilization had ever existed at all. If intelligence arises in many places, it may disappear in many places too. Civilizations rise, flourish, collapse, and vanish, leaving behind only the artifacts durable enough to survive the erosion of stars. This thought was sobering but strangely comforting. It placed humanity within a continuum, not an exception. If 3 Atlas was artificial, it meant intelligence had already happened somewhere else. If it was natural, then the solar system had still been visited by a messenger of cosmic history, moulded by forces foreign to human experience. Either way, humanity stood at a threshold facing a mystery that asked not for certainty, but for humility. During this time, a notable shift occurred in how astronomers and philosophers approached the question of detection. Traditional SETI searches rely heavily on electromagnetic signals, beacons, or transmissions. Yet the more 3i Atlas was studied, the clearer it became that the most persistent signs of intelligence might be physical, long-lived probes, objects capable of surviving the collapse of stars and the drift of millennia. A civilization avoiding the dangers of broadcasting might choose silence and observation over communication. In such a scenario, a probe could drift undetected through countless systems camouflaged by the dust. It collects its functional core wrapped in natural frost and debris. It might appear indistinguishable from a comet until one looks closely, very closely, too closely for comfort. This led to another quiet realization, that humanity's ability to detect technology disguised as nature may be extremely limited. If such probes exist, we may have seen dozens without knowing catalogued them as comets or asteroids, classified them, then forgotten them. 3i Atlas could be rare, but just as plausibly it could be typical. The only unusual thing might be the level of attention it received. The more scientists considered this possibility, the more the silence surrounding previous observations began to feel like a symptom of our expectations. Perhaps extraterrestrial technology was always imagined incorrectly, too dramatic, too obvious, too eager to meet us halfway. Perhaps the universe did not operate according to human narrative logic. During these months, as analysis papers accumulated and debates sharpened, the public conversation experienced its own strange evolution. Fear gave way to curiosity. Curiosity gave way to contemplation. A kind of philosophical quiet settled over discussions of 3i Atlas. People no longer demanded answers, they asked better questions. They wondered about time, about survival, about the lifespan of civilizations. They questioned the fragility of human knowledge and the meaning of discovery. A single object 4 kilometers long and fading into the dark had shifted something in the collective imagination. By the spring of 2026, the comet had moved so far from the sun that only the largest telescopes could still detect it. Its coma had shrunk, its tail had collapsed. Soon it would appear only as a point indistinguishable from the surrounding stars. And yet, even as its physical presence dimmed, its conceptual presence grew sharper. If it was natural, it was extraordinary. If it was artificial, it was profound. But in either case, humanity was confronted with a deeper truth. The universe is not obliged to be simple. It is not obliged to be readable. It does not owe us understanding. Sometimes it offers questions instead of answers, and sometimes the questions themselves become the revelation. 3i Atlas had become such a question, one that would follow humanity long after the object itself disappeared from view. Its meaning, whatever it was, rested not in certainty, but in the vastness of what remained unknown. As spring turned to early summer, and 3i, our Atlas, slipped farther into the dim architecture of the outer solar system, the object's faint retreat only sharpened humanity's determination to pursue it. The growing distance did not signal the end of the story, but the beginning of a new phase, and a resolve to follow it, to meet it, to see it not through telescopes but across the small gulf of space tightened by engineered trajectories. This was how the Intercept missions were born. China moved first. In December 2026, the Chinese National Space Administration announced a mission unlike any it had undertaken before a fast stripped-down probe designed not for orbit insertion or planetary study, but for a precise flyby of an object that might not be natural at all. A launch date in August 2027, an encounter in January 2029, a simple profile accelerate coast intercept but executed with the seriousness of a historic scientific effort. The probe would use Earth's gravity to slingshot outward build speed and intersect the comet at roughly 9 AU from the Sun, a distance where sunlight would be little more than a thinning memory. The spacecraft was modest in mass, unadorned in design. Cameras, spectrometers, a magnetometer, dust analyzers, no lander, no sample return, just a single intention to get close enough to see clearly. This triggered a rapid shift in the global scientific and political landscape. Within weeks of China's announcement, NASA and the European Space Agency accelerated their own plans. They had been drafting mission concepts since the first anomalies emerged, but nothing had moved beyond the sketching phase. Now the urgency solidified. Funding was redirected, design meetings condensed, proposals became commitments. By early 2027, a joint mission IR-1, the Interstellar Reconnaissance 1 probe, had been officially approved for a March 2028 launch. IR-1 would arrive months after the Chinese probe, a consequence of choosing a slower but more capable architecture. Its instruments would surpass Tianwen-4's offering, sharper imaging, more refined spectroscopy, and the possibility of a secondary CubeSat deployment. Japan offered an advanced ion engine to allow gentle trajectory adjustments, en route a way to approach more closely without compromising safety. These two missions, one lean and fast, the other precise, and layered, formed the first coordinated pursuit of an interstellar visitor in human history. Although competition shaped the urgency, collaboration shaped the long-term plan. Insights from one would inform the other. Redundancy would yield reliability. Two machines, two perspectives, two chances to resolve the mystery. Not everyone welcomed the space race dynamic. Some feared geopolitical competition would overshadow scientific integrity. Others noted that no single nation possessed the moral authority to claim an object that did not originate from Earth, especially one that might have been designed by minds older than humanity itself. But even these debates circled back to a shared truth. The comet had changed humanity's priorities. As preparations for the missions advanced, Earth's telescopes continued tracking the receding object. But by mid-2027, 3TI Atlas had dimmed to magnitude 23, barely detectable, even with the most powerful ground-based observatories. By August, when Tianwen-4 launched, the object hovered near magnitude 24, faint enough that long exposures under perfect conditions were required, and even then only the most patient instruments could extract its light from the noise. The faintness alone introduced new anxieties. What if the object underwent another acceleration event while unobserved? What if it changed course between tracking windows? What if in the long months of its outward drift, the cumulative uncertainty drifted with it like a shadow, lengthening imperceptibly until the intercept missions arrived at empty space? These concerns, though scientifically overstated, carried emotional weight. Humanity was investing billions years of preparation and a rare unity of purpose into chasing a fading light. The idea that the target might slip away unnoticed stirred a quiet fear not of danger but of meaning lost. The launch of Tianwen-4 in August 2027 became a global moment. It was not triumphant nor theatrical but solemn. Commentators spoke less of national pride and more of curiosity of humanity sending a question into the dark. The rocket rose through the atmosphere into the thinning air into the black. When the fairings separated and the spacecraft deployed, a cheer broke across Earth's networks. The probe unfurled its panels, oriented itself toward the distant coordinates where 3C Atlas would be in 18 months, and began its long departure. After the excitement faded, reality settled in 18 months of waiting, then 30 more for IR-1. During this time, 3 Atlas continued its retreat into colder space. the object's brightness decreased further until detections became sporadic. On multiple occasions, observatories lost track of it for days or weeks. Not lost in the navigational sense, its orbit remained mathematically constrained, but lost visually slipping into the limits of what our instruments could presently capture. Meanwhile, scientific conversation shifted again not toward grand theories, but toward patience. The anomalies of the comet had pushed humanity into a new phase of inquiry. The next answers would not come from Earth, nor from telescopes, nor from the careful dissection of past data. They would come from machines travelling across billions of kilometres, from sensors drifting into the shadowed outer solar system, from instruments gazing directly at whatever the object truly was. Yet even as the missions carried hope, they also carried a strange loneliness. Humanity had to accept that the comet's truth might not resolve into clarity. Even with close-up imaging, even with spectrometers and particle collectors, the object might remain ambiguous too, worn, too ancient, too damaged by time to reveal whether it had been built or born. It might be both a natural body altered long ago, or an artificial structure softened by millions of years of cosmic erosion. The possibility that ambiguity would persist, that the comet would remain a riddle even after the probes arrived, created a quiet tension that no scientific briefing could erase. But beneath that tension lay something deeper wonder. For the first time in history, humanity was pursuing not simply knowledge, but a horizon of understanding that stretched beyond immediate answers. It was chasing an object whose very ambiguity expanded the human sense of scale. It was acknowledging, perhaps for the first time, that mysteries might remain mysteries without diminishing their significance. And so, as 2027 turned to 2028, and 3 Atlas continued its silent departure, humanity did something rare. It waited together with patience, shaped by curiosity rather than fear. A world accustomed to urgency learned to live for a time with slowness, with distance, with the long arc of discovery. Because sometimes the universe offers a question so profound that the waiting becomes part of the meaning. In the months that followed, the outward drift of 3 Atlas seemed almost peaceful, like a dim ember cooling in the solar twilight. Yet beneath that calm, the scientific world was entering one of the most contentious periods in its history. The object's recession created a vacuum not of data, but of certainty, and into that vacuum stepped disagreement interpretation and the subtle gravity of paradigm shifts. It began quietly in late 2028 when a team at MIT published a reanalysis of trajectory data spanning the object's first 18 months in the solar system. Their work was meticulous, grounded in orbital mechanics rather than speculation. They revisited every recorded acceleration event, every tiny deviation, every measurement from the post-CME period, and the Jupiter flyby, removing any observation that fell below strict calibration limits. What remained was a purified mathematical skeleton of the object's path, a data set with noise stripped away. And the result was troubling. The accelerations were real, small but coherent. Too coherent, in fact. Across multiple epochs, using instruments on different continents and in different orbits, the object had repeatedly changed speed by tens of meters per second in directions aligned with its motion vector. Not always perfectly, but consistently enough that the pattern survived every statistical test. MIT's conclusion was cautious but unmistakable. Natural explanations remained possible, but required multiple layers of coincidence fragmentation at precisely the right angles, outgassing at unusually stable orientations, rotational dynamics that happened to reinforce the same thrust direction across months. The paper did not claim artificial origin. It didn't need to. The numbers spoke clearly. Atlas behaved like something adjusting itself subtly and infrequently but intentionally. The publication triggered immediate debate. Some scientists dismissed the pattern as overinterpretation. Others argued that outgassing physics for interstellar objects was poorly understood. Perhaps alien ices behaved differently, sublimated differently, or fractured differently, producing thrust patterns that only appeared directional. A third camp acknowledged the pattern but rejected its implications, insisting that improbable sequences occur naturally when data are large enough. That was true statistically. But it did little to dull the unease spreading through the field. The greatest discomfort came from the timing issue. If the object's accelerations had occurred during moments of observational density perihelion, Mars flyby Jupiter encounter, then misinterpretation would be easier to justify. But several events had occurred during periods of sparse or degraded observation where the measurements were most fragile. The question formed almost on its own: was the object accelerating when we couldn't see it clearly, or had we simply missed the mechanism behind what we could see? By early 2029, the debate had hardened into something rare in the scientific community philosophical division. One side insisted that extraordinary claims required extraordinary evidence. The other countered that extraordinary anomalies required extraordinary investigation. In between sat a quiet majority who disliked both certainty and dismissal. A group unwilling to reject the artificial hypothesis outright, yet uncomfortable embracing it without a complete dataset. Meanwhile, Tianwen 4 continued its long cruise, gliding through the dark like a single mote of intention. The Chinese probe was now only 10 months from intercept. The mission team adjusted its trajectory by fractions of a degree, refining its path using updated ephemerids of the comet's dwindling light. But even with these adjustments, uncertainties grew. The object's faintness meant that each new measurement carried a wider margin of error. In several tracking windows, the detection signal barely rose above noise. In others, the object seemed slightly brighter, but never consistently enough to draw conclusions. Some worried that the probe would miss the target. Others argued that even a near miss could return valuable data dust plasma coma structure. But the real fear, unspoken in official channels, was that Tianwen 4 would arrive to find not a comet, not a nucleus, not even debris, but nothing. One evening in April 2029, during a live-streamed panel discussion, a senior astrophysicist voiced the sentiment that had been simmering in private for months. What if the object changes course again? What if it accelerates while we're blind to it? What if it has awareness, or something equivalent to awareness of our pursuit? The comment sparked controversy, but also fascination. Because the question beneath it was unavoidable: was the object reacting? The scientific community rejected the idea of intelligence, not because it was impossible, but because it was dangerous to anchor conclusions in metaphor when only math was available. Yet the metaphor persisted not in scientific journals, but in quiet conversations in late-night emails between researchers in private Slack channels, where physicists allowed themselves to wonder without consequence. No one imagined a creature or a pilot or a mind. Instead, they imagined algorithms, automated systems, machines that conserved energy, optimized trajectories, adjusted in response to environmental changes. In that framing, the object did not need awareness, only a set of governing principles, coded perhaps billions of years ago, still operating as long as the structure held. This possibility aligned eerily with the MIT paper. Not intelligence, just consistency. By mid-2029, the idea found a foothold. If 3i Atlas was a probe, it might not be trying to hide or reveal anything. It might simply be doing what it was designed to do. Yet even that modest framing held profound implications. A probe built by another civilization, ancient or modern, distant or extinct, was still evidence of technological intelligence beyond Earth. Meanwhile, 3i Atlas continued outward silent and dim, leaving behind not clarity, but widening circles of interpretation. And as August 2029 approached, Earth waited for the first machine to reach it, not with fear, but with a suspended breath that felt planetary in scale. By late July 2029, Tianwen 4 had crossed the orbit of Saturn, drifting through a region where sunlight weakened into something thin and brittle, more memory than illumination. The probe was now weeks away from its encounter with 3i Atlas, or whatever remained of it. On Earth, the mission's updates became global events. News networks streamed the telemetry graphs. Forums erupted with countdown clocks. Even people who had never cared about astronomy before found themselves watching a small icon crawl across a simulated solar system map. But beneath the excitement, an unresolved tension hummed. No one was entirely certain where the object was anymore. Its brightness had fallen below magnitude 25 at the edge of detectability. Even the James Webb Space Telescope struggled to find it, capturing only faint smears of reflected light stretched across exposure noise. Each new measurement slightly shifted the predicted intercept coordinates. Nothing dramatic, but enough that mission planners recomputed Tianwen 4's trajectory almost weekly. And then on August 11th, 2029, 3 weeks before the flyby, the tracking residuals changed again. Not by much. A few kilometres, then a few dozen, then hundreds. Astronomers recalculated, rechecked the star fields, verified the timing. But the shift remained. The object had accelerated slightly again, aligned with its motion vector again, during a period of sparse observations. The MIT team published a brief update. The acceleration magnitude was small, but real, matching earlier patterns within error bounds. The object wasn't maneuvering exactly, but it was drifting out of purely gravitational prediction in a way that felt intentional simply because of its consistency. The public didn't need convincing. Headlines shifted instantly. Did it move is the object. Adjusting its path. Tianwen 4 might miss its target. China's space agency issued a calm statement. The probe had sufficient delta V for minor course corrections. The target was still within reach. But privately, engineers worried. Even a tiny change in trajectory at this distance, magnified across billions of kilometres, could place the object tens of thousands of kilometres from the expected flyby point. Still, Tianwen 4 pressed on, adjusting orientation, tightening its intercept arc. On August 28th, the optical navigation camera acquired its first confirmed image of 3I Atlas. It was faint, a single pale streak against black, but real. The mission's trajectory correction was initiated within hours. Telemetry updated. Flight controllers breathed again. The final approach began. The flyby. On September 3rd, 2029, 03:21, UTC Tianwen 4 crossed within 4,900 kilometres of 3I Atlas, the closest any human-built object had ever come to an interstellar visitor. The spacecraft rotated into imaging posture, opened its dust shields, and streamed compressed thumbnails back toward Earth at painfully slow bit rates. For 12 minutes, the probe was closer to the object than any telescope had ever dreamed of being. Then at a 3:33 UTC, the probe passed behind the coma, endured a brief cascade of dust impacts, and continued outward into the dark. The first image arrived 27 minutes later. It was grainy, low resolution, blurred by compression, but unmistakable. The nucleus was there, elongated, dark, structured. Even in the thumbnail, long parallel lines ran along its surface, converging near one end, diverging near the other. Too straight, too consistent, too evenly spaced to be fractures or natural erosion. Engineers in Beijing and Shanghai stared at the screen in silence as more thumbnails arrived. Scientists at MIT, ESA, Caltech and JAXA joined the live data mirrors as they refreshed frame by frame. Across the object's surface, the geometry sharpened. Not smooth geometry, not artificial in a cinematic sense, but patterned, like ribs, like longitudinal reinforcement, like architecture softened by eons. The jet vents were visible too, but they did not match known comet morphology. They emerged from symmetrical depressions, almost evenly spaced along one side, as though placed rather than formed. And then the third image arrived, the one that caused the first real shock. A segment near the terminator line where light and shadow met showed an indentation nearly circular in shape. Not a crater, not a depression. Something smoother, more uniform, with edges that curved too cleanly against the surface grain. Within 30 minutes, the global network of scientists had already begun debating whether the feature could be natural. Some insisted yes, certain exotic fragmentation models could produce repeating stresses. Others countered that nature rarely created parallel curvature across kilometres of terrain. But when the fourth image came in, the debate shifted from analysis to awe. A bright reflection glinted along one ridge, a sharp, metallic, specular reflection. It lasted for one frame only, but it was real. Dust ice, a camera artifact, compression noise. The arguments formed quickly, but none carried conviction. Because something else accompanied the reflection. A magnetic reading spike, tiny but synchronized with the moment Tianwen 4 crossed the object's magnetic axis. This was the moment the scientific community fractured. The silence begins. After the sixth image, the stream stopped. not because of suppression, but because Tanwen 4 moved beyond direct line of sight, entering a scheduled low-gain telemetry mode. The high-resolution images, the ones stored on board, would take weeks to transmit, but the thumbnails alone ignited the world. Forums crashed, newsrooms ran emergency broadcasts, scientific institutions scrambled to issue statements urging calm and caution. Yet one truth had already taken hold even before the high-resolution images arrived. Atlas was not a simple comet, and whatever it was, nature had never made anything quite like it, or at least not anything we understood. More data would come, arguments would intensify, but the shape that emerged from those thumbnails, the quiet geometry revealed for the first time, would mark the beginning of the largest scientific divide since the discovery of exoplanets. The high-resolution images began arriving on September 18, 2029, trickling in with the slow, deliberate rhythm of deep space transmission. Each frame took hours to assemble pixels returning in thin streams across billions of kilometers, like fragments of an ancient tablet being brushed clean. Yet when the first full image resolved, the global scientific community fell into an immediate and instinctive silence. The geometry was too clear to ignore. What had once appeared to be a simply elongated nucleus now revealed a pattern of structural ribs arranged with an unsettling degree of regularity. The spacing was not perfectly uniform, but it was consistent enough to evoke the logic of engineered reinforcement rather than the randomness of natural cracking. These ribs curved with the body's contour as if shaped to optimize strength, more reminiscent of aerospace fuselages or deep ocean pressure hulls than primordial rock. Nature does produce order, but seldom such convergent structural efficiency. Subsequent images added to the disturbance. A smooth circular depression, initially thought to be a shallow cavity, resolved into a recessed basin, with beveled edges and concentric interior striations. Geologists insisted it might be the remnant of a collapsed subsurface void. Engineers quietly disagreed. The symmetry was too precise, the shape too deliberate. Then a fracture running along the terminator exposed internal layering, unlike anything normally found in comets. These layers were not chaotic sediments, but thin repeated sheets of differing reflectance stacked with a consistency that suggested purposeful arrangement. Composite structures in human terms, load distribution architecture in engineering terms, or in scientific terms something that demanded explanation beyond familiar mechanisms. Efforts to preserve natural interpretations grew strained. Proposals invoked exotic stress fractures, long-duration erosional patterns, or unusual crystallization histories. But the deeper the analysis went, the more the phrase unusual natural formation began to feel like an evasive placeholder rather than a coherent model. The debate sharpened into two schools of thought, one clinging to the premise that nature, given enough time and peculiar conditions, could produce almost anything. The other arguing that the probability of so much optimized structure arising spontaneously was vanishingly small. The tension intensified when the magnetometer readings were released. For a brief 40 seconds during the flyby as Tanwen 4 passed near the object's equatorial region, the spacecraft detected a faint magnetic pulse. It was periodic, coherent, and synchronized perfectly with the comet's 8.31-hour rotation. A rotating body can carry remnant magnetization, but a modulated pulse phase locked to repeating surface geometry implies an internal arrangement of conductive materials capable of storing and releasing magnetic signatures in patterned intervals. The pulse was too weak to indicate any functioning system. It resembled the fossilized echo of a magnetic architecture long since dormant. But its alignment with rotation was statistically significant, and its profile pointed to material distributions inconsistent with simple ice rock mixtures. Within days, a technical briefing from the Chinese Academy of Sciences quantified the issue in stark terms. The likelihood of these magnetic harmonics emerging from a naturally formed body was estimated at less than 0.3% with large but meaningful uncertainties. It was not a claim of artificiality. It was a recognition that the data resisted conventional framing. Public discussion tried to keep pace with scientific caution, but the images and magnetic signatures carried their own momentum. The world had seen for the first time the interior hints of an object that behaved like a structure, an object whose geometry and pattern seemed shaped by principles rather than chance. And yet Tanwen 4 had delivered only a fraction of its total observations. More than 60 high-resolution frames remained in the transmission backlog, each promising to deepen or overturn the emerging interpretation. While the spacecraft continued sending data, anticipation spread through the scientific community with a mixture of awe, skepticism, and quiet apprehension. The possibility that the universe might be revealing an artifact rather than a fragment of rock was no longer unthinkable. It had become a hypothesis, one grounded not in imagination, but in the uncomfortable precision of returning pixels and silent magnetic echoes. Over the following weeks, the remaining images from Tanwen 4 arrived with an agonizing slowness, each one deepening the tension rather than resolving it. The initial 6 images had raised questions. The next 20 fractured the scientific consensus. As more frames completed, the elongated body of 3i Atlas revealed a surface far more intricate than any natural nucleus previously documented. The rib-like structures extended farther than expected, branching in subtle, mathematically consistent variations like harmonics in a physical form. They were not identical, but they followed a progression, each ridge slightly offset from the next, in ratios that mirrored logarithmic spirals and load distribution models familiar to structural engineers. This pattern hinted at an internal logic, as if the object had been shaped by iterative principles rather than random accretion. In other regions, the surface showed patterns of erosion that made no geological sense. Instead of chaotic pitting or sublimation scars, some areas exhibited long linear troughs running parallel to the main axis, bordered by raised edges with sharply defined boundaries. The troughs were too straight, too consistent over kilometers of terrain, resisting every attempt to explain them through thermal stresses or micrometeorite abrasion. A comet's surface is normally sculpted by sublimation and impacts processes that leave irregular, disordered features. Yet here the troughs behaved like channels, structural, not erosive, though their purpose remained entirely opaque. Then came the most unsettling discovery. Near the midpoint of the object, a depression captured in earlier frames resolved into a network of thin, angular lines beneath the frost layer. These lines formed an irregular polygonal lattice, not regular enough to resemble circuitry, not chaotic enough to resemble cracks. It was an intermediate geometry, something between structure and fracture, as though time had eroded the original design into a ghostly imprint. Spectral analysis showed faint differences in albedo along these lines, suggesting that whatever lay beneath had a different composition from the surrounding material. The scientific community found itself in a stalemate. Geologists argued that unusual fracturing could produce polygonal patterns under exotic thermal conditions. Engineers countered that the geometry was too consistent, too optimized, too suggestive of compartmentalization. For every natural explanation proposed, someone could show a measurement that undermined it. For every engineered interpretation suggested, someone could demonstrate why such features did not necessarily imply technology as humans defined it. The controversy became known as the intermediate geometry problem, a term capturing the uncomfortable ambiguity between nature and intention. As debate intensified, new data from the probe's infrared sensors complicated matters further. The thermal map revealed subtle temperature gradients across the object's surface that did not align with sunlight exposure. Some regions stayed warmer than expected, even in shadow, while others cooled unusually fast under direct illumination. These gradients were too faint to suggest active heat sources, yet too structured to be written off as random. They hinted instead at internal materials with non-uniform thermal conductivity, something one might expect from layered composites or complex subsurface architectures, but far less likely in a primitive interstellar body. By mid-October, nearly all of Tanwen 4's data had been received. The scientific world was fragmented into camps, each defending hypotheses that grew more strained with every new detail. Natural explanations began to resemble Rube Goldberg contraptions of improbabilities stacked atop assumptions. Artificial interpretations, while more coherent, required invoking intentions and civilizational histories for which no corroborating evidence existed. All the while, another spacecraft was on its way. IR-1 launched months after Tanwen 4 was larger, more capable and equipped with instruments specifically designed to resolve the ambiguities left behind. It would arrive 6 months later. Its sensors would see deeper beneath the frost map the magnetic harmonics with higher resolution and capture images at scales Tanwen 4 could not approach. The anticipation was quiet but electric, a collective holding of breath. Tanwen 4 had revealed too much to dismiss, yet too little to conclude. The truth, natural, artificial, or something stranger, remained suspended in uncertainty, waiting for IR1 to close the gap. And so the world entered another period of waiting, hovering between explanations, watching an object older than Earth drift silently through the dark, carrying within its structure a geometry that refused to reveal its origin. The months that followed unfolded with an uneasy stillness, as though the scientific world had entered a low-gravity state where every new idea drifted slowly suspended without resolution. Arm was still half a year from intercept, yet speculation grew heavier by the day. Tanwen 4 had given humanity a glimpse, a troubling, fascinating, incomplete glimpse into an object that seemed to sit precisely on the boundary between natural formation and engineered artifact. But the more closely scientists examined the data, the more that boundary blurred. The next wave of analysis focused on something easily overlooked in early excitement microstructure orientation. When researchers modelled the ribbed geometry revealed in the first high-resolution images, they found that the spacing, though imperfect, followed what appeared to be stress distribution curves. In simulations, these curves minimized torsional strain during rotation, suggesting the object had maintained structural integrity for billions of years under constant micrometeorite impacts and thermal cycling. Natural bodies rarely exhibit such long-term stability. Comets tend to fracture, shed mass, or split entirely. Yet Through-Eye Atlas, despite its enormous size, showed no major fragmentation scars, only the enigmatic ribs and troughs, which now appeared to serve the same function as reinforcement. The last coordinated Earth-based observations came in late winter, when Through-Eye Atlas sank below the brightness threshold of all but the largest telescopes. Its coma had nearly collapsed. Jets that once shone like thin luminous threads had faded into obscurity. The object now appeared as a dim elongated point slipping through, the outer dark unchanged, unhurried, indifferent to the attention it had gathered. It was moving steadily toward the region where sunlight weakens into a pale haze and the solar wind thins into silence. Out there in the cold that borders interstellar space, every motion becomes deliberate, every interaction slow and stretched, as though time itself thickens around distant objects. In the end, perhaps that is the real lesson the object offered. Not confirmation, not contact, not certainty, but perspective. A reminder that cosmic truth is not always loud. Sometimes it's found in the faintest motion of a dim object receding into the night, something ancient, something enduring, something that asks only that we pay attention. And in that quiet humanity waited breathing in the darkness between stars, ready at last to listen. Traveller, if you've stayed with me this far, you've drifted through a long night of data silence and starlight. And now, as Three-Eye Atlas fades into the outer dark, something in us settles as well. Not with answers, but with a deeper awareness of how vast the unknown truly is. Out there, the object continues its slow escape, carrying whatever truth it holds into regions where human eyes cannot follow. And here on this small world, we continue our own quiet orbit, measuring, wondering, listening. That is all we can do, and perhaps all we were ever meant to do. Because sometimes the universe offers clarity, and sometimes it offers only a question wrapped in cosmic dust. But that is enough, listener, to witness, to think, to imagine, to stay open to possibilities larger than ourselves. You're not lost in this mystery, you are part of it, woven into the same laws of gravity and time that guide every wandering fragment of interstellar stone. And as the object moves into silence, let that silence be a comfort, not an absence. A reminder that the universe does not rush. It reveals itself in its own time, and only to those patient enough to keep looking up. Rest now, observer. Let your thoughts dim like a comet slipping beyond the heliopause. Let the cosmos keep watch a little longer. Stay curious. Sleep well, traveller.